Okay, so question 14. The structure of 4 molecules are shown below. All right, and they say which 2 molecules belong to the same homologous series. So they're checking again, they want you to see, or they want to see if you recognize when you have different compounds of the same homologous series. All right, so you look at the first one, this is C double bond OOH as 1. Then this has a OH group. So this here is a carboxylic acid. This here is an alcohol. The third one is an alkene. And the fourth one is a carboxylic acid, C double bond OOH. So P and S both belong to the same homologous series of carboxylic acid. So the answer is B, P, and S. They both belong to the same homologous series, which is carboxylic acids. All right, so let's move forward. So next thing, structural isomers. So the question comes up, what are isomers? What are structural isomers? Structural isomers, these are molecules with the same molecular formula, but different molecular structure. They have the same molecular formula, molecules with the same molecular formula, but different molecular structure. So for example, you have C2H6O. In the first one, you have carbon bonded to 3 hydrogens. The second carbon is bonded to 2 hydrogens, which is bonded to oxygen and a hydrogen. This makes this compound 1,2-met-eth, so this is ethanol. Right? On the other hand, we have CH3 on one side. You have carbon bonded to 3 hydrogens. This is bonded to oxygen, which is bonded to carbon that is bonded to 3 hydrogens. Right? This results in the formation of an ether. Right? And this is a methyl group, so it's dimethyl ether. So these two compounds that are formed, even though they have the same number of carbons, hydrogens, and oxygens, depending on where the oxygen is located, would determine what that compound is, right? These are two different compounds, but they have the same molecular formula, except they have a different structural formula. So what does that have to do with anything? Structural isomerism, they have the same chemical formula, but different structural formula. They could either be branched or unbranched. So for example, there are 2 alkanes with 4 carbon atoms. So we could either have 1, 2, 3, and then on the second carbon, we could have a carbon above it. So this means that a branch structure would have been produced, right? And branch is its name, meaning that there is a branch that can be derived from the main chain, while on this side here we have 4 carbons, 1 bonded to each other in a straight line. So this here is bonded in the form like a T, upside down T, and this here the carbons are all bonded in a straight line. Branch isomers have lower boiling points, and this is because branches prevent the molecule from getting close together, resulting in weaker attractions, and they tend to be less flammable. All right, so they have lower boiling points because the branches prevent the molecules from getting closer together. All right. So far, I trust that this is making sense, guys, and you're understanding. Next, we have structural isomerism. Compounds with the same molecular formula exist in different forms due to arrangements of atoms. So we can see this from the example below. So here, in this here, what you would have had on the inside, you would have had a carbon here, and carbon here. Carbon is in the middle here of these structures. So with that, On this one, we have the OH group bonded to the carbon on the end, but in this second structure, the OH group is bonded to the carbon in the middle. Right? Which means to say that even though they have the same number of carbons, hydrogens, and oxygens, they have different structural arrangement or different structural formula. All right, so let's move along. All right, so it could either be a straight chain, as I showed you earlier, or it could be a branch chain. So where we have the carbon that is bonded onto another carbon that is not a part of the main chain. All right, so let's take a look at a question or two. The alcohol form a homologous series. The first 5 members are given in the table below. You have methanol, ethanol, propan 1-ol, butan 1-ol, pentan 1-ol, and they show the formula for the methanol, CH3OH, ethanol, CH3, CH2OH. Then they skip propanol, and then they have butan 1-ol, CH3, CH2, CH2, CH2OH, and then they have pentan 1-ol, CH3, CH2, 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 CH2OH. They show you the energy given off for the heat of combustion. All right, so these are complete the table below, right? So for the propanol, you'll have met at prop, you're supposed to have 3 carbons, so you're supposed to have CH3, CH2, CH2, OH. All right, that's supposed to be the formula. CH3, CH2, CH2, OH. Right, there's supposed to be 2 CH2 groups, 1 CH3 group, and the OH group. Right, the heat of combustion or the energy that is given off from propanol, it's usually between 2030 to 2050. It should not be a number that is below 1380, and it shouldn't be a number that is above 2680. Right? It shouldn't be higher than butanol, and it shouldn't be lower than ethanol. It's supposed to be a value somewhere in the middle there. So any value between 2030 and 2050 would be fine. All right, next part of the question. Complete the equation for the combustion of pentan 1-ol in excess oxygen. Anytime an organic compound undergoes combustion, it produces carbon dioxide and water. Carbon dioxide and water. So I have 5 carbons over there. So I would want 5 carbons on this side. I have 11 and 1 is 12 hydrogens over here. I want 12 hydrogens over here, which means to say I have 5 2s are 10 oxygen, 10 and 6 is 16 oxygen. All right, no, 5 2s are 10. O2 by 5, that is 10. 10 by 6 is 16. So I can have 8 O2 if it's in excess oxygen. 8 2s are no. I have an oxygen here. So I can't put 8. I need to account for the oxygen. I need to have 7.5 oxygens. 7.5. 7.5 by 2. 7.5 by 2, that will give me 14 plus 1 is 15 plus 1 will give me 16. So this here would give me 15 oxygens, and this one here would make it 16. So 7.5. So the balance equation is supposed to be 7.5 oxygens to give me 5 molecules of carbon dioxide and 6 molecules of water. All right. The next part of the question asks, state 3 characteristics of the homologous series other than the variation of physical properties down the series, right? There are a number of different options you could choose from, right? So any tree, you could have the same general formula, same functional group, same chemical properties, same methods of preparation, right? Consecutive members differ by a CH2 group, all that's acceptable. Any of those things, any three of those you could have chosen for your answer in trying to identify the properties of the same homologous series. Next question. The following alcohols are isomers: CH3, CH2, CH2, CH2OH, and CH3 in brackets 2, CH, CH2OH. The question say, explain why they are isomers. The reason why they are isomers is because they have the same molecular formula, but different structural formula, different structural arrangement. They have the same molecular formula. The reason why they're isomers, they have the same molecular formula, but different structural formula, different structural arrangement. So they ask you to draw the structural formula of another isomer of the above alcohol, right? All you have to simply do, depending on the one that you choose, is just move the OH group from the end to one of the other carbons in the middle, right? If you decide to do that one, right, you move this OH group from here and you put it on one of these carbons in the middle here, right? And that would have a different structural arrangement, but it will have the same number of carbons, hydrogens, and oxygens. Or if you decided to use this one, you could have moved one of these groups from here, and instead of having a CH group bonded to a CH2 group, you could have CH3 by 3 bonded to carbon to OH group. So I'll have one CH group, and this is bonded to another, the carbon, which is bonded to another CH3 group here. 1, 2, 3, which is bonded to another carbon that is bonded to another CH3 group here. 1, 2, 3, and then that is bonded to OH. Right now, at the advanced level, this is referred to as a tertiary alcohol. Right? There's one CH3 group here, one CH3 group here, one CH3 group here, which accounts for the 3 CH3 groups that is bonded to the carbon, which is bonded to OH. All right, all I want you to do right now, guys, is just follow what I'm saying, all right, so that this can make some kind of semblance of sense. All right, so next question. Petroleum-based diesel is a mixture of hydrocarbons such as octane and octene. Oct means 8 carbon atoms per molecule, and they ask you to draw a structural formula of an octene molecule. All right, now, what I've shown you is the skeletal formula, the displayed formula, and actual representation of what the molecule could look like if you were trying to display it. So this here is the skeletal formula. Oct meaning 8, so I'll have one carbon there, another carbon is here, a carbon is there, a carbon is here, a carbon is there, a carbon is here, a carbon is there. Right? Are these carbons here, each one of them, there are 2 hydrogens bonded to it. So hydrogen is bonded to it. So I have CH2 bonded to CH, which is bonded to carbon here. And this would have been CH2, which is bonded to CH2, to another CH2, to another CH2, to another CH2, to a CH3 group, all right? And this has 1, 2, 3, 4, 5, 6, 7, 8 carbons. They say to draw it for octene, so it means to say it's an alkene. There's a double bond at the start here to signify that we're dealing with an alkene, right? And I showed you the displayed structure, which is right below it, right? And you can see carbons 1 to 8, and you see all the hydrogens are bonded around the carbons. And then on the side here, I'm showing you the different carbons. So the fat black spot represents, this part here represents the carbon. This represents the carbon, 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 carbon. And the gray parts represents the hydrogen that is bonded to those carbons. So this here represents the hydrogen. This here represents hydrogen. Hydrogen that is bonded to it. Hydrogen is bonded to it. All right, so the next thing they asked us to do is describe a test which would distinguish between octane and octene. In essence, they're asking us to describe a test to distinguish between an alkane and an alkene, right? There are two simple tests that we could use. The tests, we could add the bromine water, bromine in an organic solvent. The results, octane remains brown orange, right? Octane with bromine water, it does not show any change. And the reason for that is because the alkane has no double bonds present. However, the octene goes from the brown yellow color to decolorizing or colorless. So this here should be octene. The octene goes from the brown yellow color to colorless. It decolorizes. And that helps us to distinguish between an alkane and an alkene. Right? The next test that is used is using KMNO4. With an alkane, it stays purple. Potassium permanganate is purple in color. With an alkane, it remains purple. So with octane, it would stay purple, but with octene, it will go from purple to colorless. It will decolorize with the alkene. So you could either use bromine water in the presence of an organic solvent, or you could use potassium permanganate in the presence of an acid or alkaline. Right? With the alkane, it shows no change, meaning that it remains the color of the reagent, which is either bromine water, which is a brown orange or brown red color. And with the KMNO4, potassium permanganate is purple, it remains purple in color. All right, so moving on. Next. The alcohols form a homologous series. The first member is methanol and the fourth is butanol. The question asks, give two general characteristics of a homologous series. So by now you're beginning to see patterns developing when it comes to homologous series. They have the same general molecular formula, they have the same functional group, same physical properties, they show similar trends. So the boiling point increases as the number of carbons present also increases. They have similar chemical properties, and the same method is used, generally speaking, when trying to prepare them. All right, so as you go from methanol to propanol to butanol to pentanol to hexanol, right, they are telling you they have the same molecular formula. They have the same functional group, which is alcohols, OH group, right? They have the same physical properties, so they show similar trends, right? The boiling point increases as you go down the group. So as you move from met 1 carbon to et to 2 carbons to prop to 3 carbons, the boiling point also increases. They have similar chemical properties and they use similar methods or the same method to prepare them. All right, so the next question asks us to calculate the mass of 1 mole of C8 alcohol, right? So if we want to calculate the mass of 1 mole of an alcohol, right? The alcohol, 8 carbons, so I'll have Ca times to 17 hydrogens, right? Plus OH, right? And it comes from the general formula CnH2n plus 1 OH, right? So if C is 8, 8 by 2 is 16 plus 1 is 17. That's how we end up with C8H17 plus OH, right? So to find the mass of 1 mole of that, you can find out how much is carbon. Carbon is 12. 12 by 8 is 96. 17 hydrogens. 17 by 1 is 17. Plus 1 oxygen. Oxygen is 16. Plus a hydrogen, which is 1. All right, so 96 and 10 is 106. 106 plus 10 is 116. 616 plus 6 is 122. 122 and 1 is 123 plus 7 is 130. All right, I believe that's supposed to be correct. Yes, which corresponds to what they have there. So the mass of 1 mole of C8 alcohol is supposed to be 130 grams. All right, all I did is I added up how much of each element is present by finding the molar mass of each of the elements by the number of times that element appears, and then I add up the answers for all of them, and that gave me my answer. All right, so all right, so we're moving on to the next thing that I want to cover. All right, hopefully I could get to finish everything that I want to finish within this time. It's only a couple more slides, people. Once we get through this, I think we should be fine. So let's go again.
So, if I were to characterize organic chemistry and base it around a single element, it would be carbon. And I'm going to use living organisms to introduce organic chemistry. So in other videos or textbooks, they tend to use crude oil, but I tend to associate things that are closer to us. So in this video, I use living organisms to introduce organic chemistry. So living organisms are made primarily of carbon. So most compounds, or you'll find a prevalent number of compounds inside us and other living beings, and they will be made of carbon, such as amino acids, which basically make up protein. Okay, so carbon compounds, as a result, are very versatile, and this is because the carbon atom has 4 available bonding electrons in its valence outer shell, so it can form 4 different types of bonds and 4 different types of configurations. So therefore, it can form a multitude, a massive amount of configurations to form very, very different carbon compounds. So this is why they are very versatile. So carbon can form bonds with other atoms such as hydrogen, oxygen, and nitrogen. So these 3 compounds are very common to form bonds with carbon. But additionally, carbon can also form bonds with other carbon atoms to form basically very long chains or branch chains of carbon atoms, okay? So the fact that carbon is able to bond with different atoms as well as carbon itself allows living beings to have such huge variety, okay? So, if I such as hydrogen, oxygen, and nitrogen, so these three compounds are very common to form bonds with carbon. But additionally, carbon can also form bonds with other carbon atoms to form basically very long chains or branch chains of carbon atoms, okay? So the fact that carbon is able to bond with different atoms as well as carbon itself allows living beings to have such huge variety, okay? So now we talk about a very, very important concept in organic chemistry, and that is the CH group. So in all living beings, there will always be carbon compounds which contain the CH bond. And what's great about the CH bond is that it will help us separate between compounds which are not organic and compounds which are organic. So we characterize it as the CH group, which is basically a group containing the carbon atom, the hydrogen atom, and the two electrons which form a covalent bond between them. That's all it is. And as I said, it helps us separate separates compounds that are organic and not organic, and it will help us define organic chemistry. So organic chemistry is basically the study of compounds which contain this group. Therefore, organic compounds are basically compounds which contain the CH group. Okay? Cool. Now we go to learning about how to describe organic compounds. And a first step to describing organic compounds is having a symbolic way in which we can describe them. So we commonly use formulae to describe organic compounds. So there are three main different types of formulae. There are actually four, but we'll talk about the fourth one, which is the general formula under homologous series. Okay, so three main formulae to describe any organic compound. So the first one is the molecular formula, and then you have the structural formula, and then you have the displayed formula. And I will talk into detail about each formula. So the first is the molecular formula. You probably have seen this before. So a molecular formula is basically a formula that will display the exact number of atoms of each element in the compound. So for example, we will use the example on the left, which is ethane, which is a compound which contains 2 carbon atoms and 6 hydrogen atoms bonded in this covalent compound. So therefore, the molecular formula is simply C2H6, where 2 is the number of carbon atoms and 6 is the number of hydrogen atoms. Now let's look at the structural formula, which is basically the same as the molecular formula. However, it splits all carbon atoms in the formula into its separate positions so that all the surrounding atoms around each carbon atom are put separately. So in other words, for this example, the first carbon atom is represented as C, and the first 3 hydrogen atoms which surround it are H3. So we have the formula as CH3 followed by CH3 again, which represent the second carbon atom surrounded by the second set of hydrogen atoms. Okay, so the total or the whole structural formula which describes ethane is CH3CH3. Okay, now let's look at the easiest formula, which is the display formula, which is basically the structural formula, but it shows all of the bonds, all of the covalent bonds, and the arrangements of the bonds surrounding each of the carbon atoms. Okay, So those are basically the three main formula you can use to describe any organic compound. So let's look at a concept, as I mentioned briefly, the homologous series. Okay, so in organic chemistry, in our IGC's organic chemistry, you will learn about four main groups of organic compounds. The first being the alkanes family, second being the alkenes family, third being the alcohols family, and the carboxylic acids. There may be reactions between members of each of these families, but we will talk about that in a much later video. Okay, so homologous series. Right. Each of the organic groups of compounds are known as a homologous series. So the alkanes family is known as a homologous series. So all alkanes they belong to a homologous series called the alkanes. So all alkenes belong to a homologous series groups of alkenes, and so on. So homologous series is basically a fancy way of saying a group of organic compounds. And what the great thing is for each homologous series they share similar characteristics. So all members of a homologous series will have the same functional group, which are basically responsible for the chemical properties. Don't worry about this. All three of these bullet pointed I will describe in detail in the next couple of slides. Okay, so they will have the same functional group, which will determine their chemical properties, and since they have the same functional groups, they will have similar chemical properties, or they will react the same way to other atoms or on its own. Next, they will show a gradual change in physical properties, which in other words means is that members in a homologous series will have very, very similar physical properties, but they will only differ by the number of carbon atoms in its chain. And of course, these examples I will mention in very much detail when I talk about or make a video about each homologous series in much more detail later on. And they will have the same general formula, which is basically a formula used to symbolically describe any organic compound within a homologous series. So let's look at what I mean by them having the same functional group. A functional group is basically a group of atoms which are responsible for all chemical reactions involved in the members of a homologous series. So for example, in the alkanes homologous series, the CH group is responsible for all chemical reactions. In the alkenes, this carbon-carbon double bond group is responsible for all reactions in the alkenes. In the alcohols group, the OH bond connected to the carbon bond will be responsible for all chemical reactions for alcohols. And in carboxylic acid groups, the COOH or the COHO will be responsible for all chemical reactions involving carboxylic acids. Okay, so as a result, they are responsible for the chemical properties which make each homologous series different from each other. So when I talk about them showing a gradual change in physical properties, or they're showing similar physical properties, but they depend on the number of carbon atoms in the chain, what I mean is that the physical properties of the members of the homologous series will depend on the number of carbon atoms within the chain. So for example, let's use the boiling point of the members of a homologous series as an example. So as you can see, for alkanes, as you increase the number of carbon atoms in the chain, the boiling point of each compound will increase very predictably in a straight line. So we call this a gradual change in physical properties, and these changes, as you can see, will apply for alkenes, alcohols, and carboxylic acids. So in all organic compounds, the physical properties will be very, very predictable based on its homologous series and its number of carbons in its chain. Okay, so the last concept that I talked briefly in homologous series is the general formula. The general formula is basically a formula involving a variable n, which is able to describe or name a molecular formula for all members of the homologous series. So for example, looking at the alkane group, the general formula is CnH2n plus 2. So in this case, we have ethane, so if you plug in the N as 2, you end up with the molecule correctly as C2H6. So based on the number N, which most of the time will be the number of carbon atoms, you will basically have the molecular formula to all members of the homologous series.
All right, so that basically was a recap of some of the things that we talked about, right? Before we move forward. The next objective is objective 14.4, right, which tells us to describe the properties of alkenes, describe the bonding of alkenes, and describe substitution reactions of alkenes with chlorine, right? Those are some things that we want to look at. Let me see how. All right, I'll come back to this video, and I think both of them are to come back to. All right, so when we talk about the properties of alkenes, alkenes are generally unreactive, right? Except when we're referring to them as burning. When we're trying to combust them, alkenes are generally unreactive. When we try to describe the bonding in alkenes, right, there are no double bonds present in alkenes. There are no carbon-carbon double bonds. Therefore, the carbons are said to be saturated because they each form 4 single bonds. Right? That is to say, the bonds, as they form it, they try to form as many as possible. So they could have either carbon-carbon bonds or they could have carbon-hydrogen bonds. But all these bonds are single covalent bonds, right? They are single covalent bonds. They have the general formula CnH2n plus 2, right? That's the general formula that they have. So for example, if I had ethane, Et meaning 2 carbons, N is 2, C by 2, and the hydrogen would be 2 multiplied by 2 plus 2, which is 2 2s are 4 plus 2 is 6. So the molecular formula of ethane would be C2H6, right? The alkane molecule can be represented by the molecular formula C2H6. We could have the displayed formula where we show the actual number of carbons and hydrogens, and we show the covalent bonds, right? What you should know, the first 4 alkanes are methane, ethane, propane, and butane. All right, in exactly 60 seconds, of course, it's going to cut off again, and I'll ask you to log back in for the last time before we end. Right? Then they tell us to describe substitution reactions of alkenes and alkenes with chlorines. Right? When you log back in, there are some videos that I want you to see, right? That I want you to look at. So once it stops, I just want you to log back in once more. All right, just allow me to engage you for about 15 more minutes before we end today's lesson, and then we will call it a day.